In this video, we're going to look at understanding and then using the second fundamental theorem of calculus. So to work on the creation of that understanding, we're going to consider the definite integral as a number. And given most of our experiences, we've evaluated a definite integral as it goes from one number to another, so from one constant to another. So if it is to represent a number, a and b are constants, and our function would be written in terms of some variable. So here, what we're most used to is a function of x. So as we move away from that and we start to, instead of looking at this as a number, we'll begin to look at it as a function of x. So in other words, when we go to evaluate this definite integral, we're looking at it as a function of x. So notice our x value here, this variable, is our upper bound. So our upper bound becomes some sort of a variable expression. What is important is that our lower bound is a constant. It must be a constant. And lastly, the function that we're looking at the definite integral of is a variable different than the one that it is noted to be in terms of. So to illustrate this, we're going to look at this definite integral, evaluating the function capital F of x. So we're going to go from 0 to this variable x of cosine t dt, and then we're going to evaluate this function at these three different x values. So you can appreciate, instead of looking at this as three separate problems, we're going to leave this variable intact. So we recognize that when we go to evaluate what is to be a definite integral, we're going to go ahead and integrate this cosine function, and that is going to give us sine of t. So remember, sine of t, the derivative of sine of t is cosine of t. So integrating is that anti-differentiation process. And then we're going to make use of that first fundamental theorem of calculus, where we'll take our f of b, if you will, so plugging x into our function, and subtracting from it f of a, so taking that lower bound and plugging it in. And the sine function at 0 is 0, so really our, if you will, capital F of x function is simply sine x. So again, you can appreciate, instead of saying evaluate this definite integral as we go from 0 to 0 of cosine t dt, and then doing it again from 0 to pi over 4, and a third time from 0 to pi over 2, we really only need to integrate once, and then from there take that function and evaluate it at those three different values for x. So we know that sine at 0 is 0, which should make sense, because if this integral went from 0 to 0, that sum, that value should be 0. The sine function at pi over 4 is the square root of 2 over 2. And then lastly, the sine function, when we evaluate it at pi over 2, should give us back the value of 1. So you can appreciate the, I guess, niceness of looking at this integral more so as a function as opposed to always just one constant. So as we move into this second fundamental theorem of calculus, if f is a continuous function on an open interval I containing a, so again containing this constant, and again stressing this constant is going to be the lower bound to our function. Then for every x in the interval, if we take the derivative of our integral as we move from a constant to some variable x, or some variable expression written in terms of x, of this lowercase f of t dt, then what we would get back is the function written in terms of x. So it seems quite odd, but hopefully it makes sense that when we integrate, we're finding the antiderivative of f. So if you will, we are finding this capital F of x function that we evaluate from a to x. Or I really should have this t in here. So now when we go to rewrite this piece, that would give us capital F of x minus f of a. So we have a function, and with it we would know a constant that we're subtracting from it, because remember a is a constant, and plugging that into our function we would get back some number value. Well, what this is telling us to do then is to take this, and we're going to carry this d over dx down. So essentially I would have that d over dx here. And remember, d over dx is telling us to take the derivative of this expression in terms of x. Well, if I just went from lowercase f to uppercase by integrating it, that is finding the antiderivative, and then I go back and I take the derivative of this function, I should get back a lowercase. I should get back the original function that I had, but now it would essentially be written in terms of x, and the derivative of any constant would be 0. So let us consider this example here to illustrate. And I'm going to go back and say, suppose I don't really understand this second fundamental theorem of calculus. I feel I could go back on my prior knowledge of integrals. So if my function, capital F, is written this way or described this way, and I had to find its derivative, I would first go through that process of integration. So the integration would give us that sine of t. The derivative of sine is cosine. And we would evaluate that from pi over 6 to this x to the power 4. This would be my function f of x. So I will take that upper bound and plug it in. So in other words, I would have sine of x to the 4th power, and I would subtract from it sine at pi over 6. We would be able to replace this sine at pi over 6 with 1/2. Now, as a reminder, this x to the power 4, this x to the 4th, is just the angle to this sine function. So you may find it helpful to put it in parentheses. So this is my f of x function, but I was asked to find the derivative of this function. So we'll go back on our differentiation rules. The derivative of this trigonometric function, we want to call on the idea that it is one function, x to the power 4, tucked inside of this trigonometric function. So we have a composition of functions. We will differentiate the outer function first. The derivative of sine is cosine, and the angle stays the same. So that inner function stays the same. And then we would multiply by the derivative of this inner function. So the derivative of x to the 4th is 4x cubed. So our derivative is, rewriting it, 4x cubed in the front times cosine of x to the 4th power. So My question to you is, do I really have to go through this process every single time to evaluate the derivative of this function when it is described as an integral? And that answer is no, I do not have to go through this process every single time. Instead, what I'm going to recognize is that when I go to take the derivative of an integral, I'm recognizing that I am supposed to get this function back. And hopefully that makes sense, because the integration, the antiderivative of cosine is sine, so when I differentiate back, I get back cosine. So the fast way of doing this problem is to, number one, recognize that this function, the primary function, the outer function, if you will remain the same. And as we look at the process of integration, we had to make sure the constant was on the bottom, and it was. And this x to the power 4 was plugged into this antiderivative. So we ended up with a function inside of a function. And again, minusing then this constant. When I go to differentiate, I've got to realize that this x to the 4th, this upper bound, is then being inserted into this outer function of cosine. So that function becomes then the inner function to the primary function of the problem. And with that, when we go through, so that's this piece here that we currently have in this upper piece. What we have left to do is differentiating this now inner function, or in other words, differentiating what that upper bound was. So again, the derivative of x to the 4th is 4x cubed. And now you can see those answers are the same. So to recap, when you have to take the derivative of an integral, you are going to, step 1, confirm that the lower bound is a constant. So step 1, confirm the lower bound is a constant. Step 2, recognize that this is some variable expression, and what you're going to do is you're going to take that variable expression and replace it with each variable within the function that you're having to integrate. And here we plugged it in. And with that, once you have plugged it in, you will then multiply this primary function with the new function inserted by the derivative of that inner function, or the derivative of that upper bound. So we'll go ahead and apply this concept to the next couple of problems. So here we have, and we'll now take the derivative with respect to t. Notice t is this upper bound, and this function is written in terms of x. So step 1, is the constant on the bottom? Yes. Step 2, we're going to take this variable expression, it just happens to be a t, and we're going to replace it with every variable expression that follows that integral. So at that, we would have the square root of t squared plus 1. And then we would multiply by the derivative of t, and the derivative of t is 1, so really no need to write this value of 1. Our derivative of our integral will be the square root of the quantity t squared plus 1. We'll go now to this example 9. Find f prime of t if f of t is this integral. And I feel I have an issue right away, because my lower bound is the variable expression and the upper bound is this constant. So we will have to apply our rule to flip, if you will, the upper bound and the lower bound. So we'll place the -3 on the bottom and the t on the top. And remember, when we change that order, we then have to negate the value of that integral, and everything else here can stay the same. So my step 1, I have now taken care of the fact that the constant needed to be on the bottom. The next step is to take this t and we will plug it into this function. So I'm going to carry this negative down. I am going to note that it is sine squared, no longer x, but sine squared t. And then we'll take this t value and we'll multiply by the derivative, and the derivative of t is 1, and so the order of multiplication does not matter. That final answer is still going to be that negative sine squared t. So checking to make sure if the constant is not on the bottom, make sure that it is placed on the bottom and you negate that integral. So on this next example, we'll start to change this variable expression, and we will then now take the derivative with respect to t for the integral as we go from 0 to t squared now of this cosine of x squared dx. So the constant is on the bottom. Check. We will now take this t squared and we are going to plug it into this function. This will now read cosine t squared, and then we're going to carry this square over because that quantity had to be squared. And now that we've plugged this upper bound into our current function, we are going to multiply by the derivative of t squared. And the derivative of t squared is 2t. My last step that I will want to do is to go ahead and clean this up, simplify it. I like the 2t brought out into the front so that we don't confuse it with the angle. And t squared, quantity squared there, is going to be cosine, and our angle will be t to the 4th power. And you're done. That is the derivative of this integral when it is written as a function. Our last example for this video is what happens when your upper bound and your lower bound both are variable expressions and that we don't have a constant. Well, our job then is to rewrite. So we are going to take the derivative of the following, and that is we're going to keep our lower bound at -2t. And if you think about for this problem, and it really doesn't matter whether it's negative and positive or vice versa, but we're going to look at this -2t moving to a positive t. And one of the most natural breaks as we move from negative to positive is going to be this value of 0. The choice, the constant that you choose to use is not really going to matter much, but I think 0 is probably your most common as a natural break in between the two functions, or between these two variable expressions. We're then going to go ahead and write this function. And to it, we are going to add, and we're going to take this integral, and where this piece left off, this next integral is going to pick up, and that's going to become that lower bound. And then we'll copy this upper bound from the original problem, and again, copy that function down. So now you can see that we do still have this integral as it moves from -2t, the initial lower bound, to this positive t, that final upper bound, and then finding something to connect in between the two. So we can now begin the process of differentiating these two integrals. And we'll go back to, again, that's step one. Is the constant on the bottom? And for this first integral, it is not, but for the second one, it is. So I will go ahead and rewrite this first integral, interchanging the upper bound and the lower bound, meaning I have to negate the value of that integral. And after I do that, I can go ahead and copy everything down from the line above. And now, taking the derivative of our two integrals, the constants are on the bottom. I will take this negative, bring it down. I will replace the x in this expression with a negative 2t. So I will have then 1 plus and negative 2t times another negative 2t is a positive 4t squared. So again, all we did was take this expression and we plugged it in for this variable. And when I simplify a negative 2t times another negative 2t, I get this positive 4t squared. Plus, and we'll do the same thing for this piece here. Again, that constant was on the bottom. And I realize at this point that I did just forget to do something. I hope you said, well, wait a second. You need to go back and you need to multiply by the derivative of that upper bound. So going back, I do have to take this expression and multiply it by what? Yes, I have to multiply it by a negative 2. So I will go back and multiply this expression by a negative 2. So let's recap really quickly. The constant was on the bottom. I have to take the negative 2t and plug it in for that value of x. So that was copied down, the 1 was copied down, and the denominator was rewritten with this 4t squared. And then you are to multiply by the derivative of that upper bound, which is negative 2. And now we can move on to this next piece. Again, the constant is on the bottom. The variable expression is on the top. We'll be able to take and plug in that value of t everywhere we have an x, which is just in this one place. And then we would multiply by the derivative of t, or multiply by that value of 1. So with that, we can then note what our final answer should be. And that is this. 2 divided by the quantity of 1 plus 4t squared plus 1 divided by the quantity of 1 plus t squared. And with that, you have an example where both the lower bound and upper bound were variable expressions.